Okay, so let's take a look at this illustration. Okay, wherein we have here the distance in between the two balls would be y. And for example, we have we have ball A here. Then it has an upward velocity, VA. And then you have ball B with a downward velocity, VB. Now, they will collide. Then afterwards, they will bounce back. We are going to consider two frames wherein we have here an observation from S frame and then an observation from S prime frame, wherein S prime frame is our reference point which is moving. So how are we going to express their velocities and their momentum? So take note here that velocity A is equal to the velocity B prime, or the final velocity of B. So they have the same initial velocities too. Then after colliding, VA is equal to VB prime. Then let's take a look at the distance that each will cover. Okay, take note we have here velocity equals distance over time. Now, if we are going to consider the round trip travel of ball A, so it will travel upward and then downward. So the round trip will be 1/2 y times 2. So let's take a look at the velocity of A. The distance it will cover will be half of y. However, since it will bounce back, that will be twice. Okay, divided by, if we are going to consider at S frame, so that will be the proper time T naught. Take note, this is according to S frame. So we have here the velocity of A is equivalent to 2 y over 2 divided by T naught. So we can now cancel out 2. So we now have here VA is equivalent to y over proper time T naught. So that's our velocity for A. Then you can also express the proper time in terms of VA. So proper time now is just equivalent to y divided by VA. So that is our equation based on S frame. Then now let's solve for the equation for VB, or for ball B. Okay, now let's take a look at the motion of ball B in terms of S prime frame, or this one, it's the moving frame of reference. So let's have, again, velocity equals distance over time. But for this time, we are looking for the velocity of ball B, so VB prime, equals the distance it has traveled, so it's the same. For a round trip, it will travel 1/2 y, and then it will bounce back 1/2 y again. So that will be 2 1/2 y. According to S prime frame, so this is according to S prime frame. In the previous example, that is according to S frame. So here, according to S prime frame, the time is also the proper time T naught. So we have VB prime is equal to y over T naught according to S prime frame. So it's important to note that this is according to S prime. So if we are going to express proper time, we also have an equation wherein T naught, proper time, so in S prime frame, we have T naught equals y divided by V B prime. So that is our expression of proper time in S prime frame. Okay? So let's continue. So let's take a look at this equation. Again, the velocity, or again, ball B is at S prime frame. So we were able to express its velocity in the earlier slide. And now we are going to check it according to S frame. So S frame, take note also that S frame is at rest. And then we have S prime frame, okay, moving at a velocity v. Prime, where ball B is found in the S prime frame, and then ball A is found in the S prime. Then they were released and then they collided. Then let's take a look at how we can express now the velocity of B or ball B according to S, or according to S frame. Okay, for S frame, we have velocity B equals the distance. As I have mentioned, it will travel twice 1/2 y. But this time, the time is no longer proper time because the S prime frame is moving relative to S. Our observer is at S time t instead of proper time. So tandaan nyo, pag sinabi nating proper time, that means that the object is at rest relative to the observer. That's why we have ball A at S frame is considered to be that's why we have ball A at S frame, we consider proper time t naught. Then we consider also a ball B at S prime frame, the proper time is also t naught. But this time we are looking at the velocity of B or ball B found in the S prime frame, but according to the observer in the S frame, which is at rest. Kaya we will consider time t. Hindi siya t naught, not at the proper time. Okay? So solving this one further, we now have, from time dilation, take note that we have t equals t naught divided by square root of 1 minus v squared over c squared. So we can use this relationship wherein we have now the velocity b. Okay, we can now express velocity b. This is according to S frame. Our velocity b is y divided by t naught over square root of 1 minus v squared over c squared. Okay? So solving this one further, we will have a velocity b. Okay, I will use this one. Velocity b equals 2 1/2 y, so that will just be y, divided by t naught, then multiplied by square root of 1 minus v squared over c squared. Kasi that will be y divided by t naught divided by 1 minus v squared over c squared. So we just get the reciprocal. So we now have here the velocity of ball B is equivalent to y times square root of 1 minus v squared over c squared equals t naught, or our velocity b now, according to S frame, equals y square root of 1 minus v squared over c squared divided by t naught, or the proper time. So solving this one further, we can now look into the momentum. So let's take a look at the momentum. Looking at the momentum for A, we have P A equals MAVA, wherein we have solved earlier that we have now MA. Our VA is expressed as Y divided by T naught. Okay, this is again according to S frame. So that will be our momentum for object A. But for object B, our momentum is PB is equivalent to MB VB. So that will become MB, and then we use this expression. So we have y square root of 1 minus v squared over c squared divided by t naught. So again, this is our momentum for object A. According to S frame, PA equals MA y over T naught. And then also, same frame, according to S frame, we have here momentum of B equals MBVB. And then let's substitute that velocity. We have y square root of 1 minus v squared over c squared over T naught. Okay, so now let's analyze this one. Okay, do you think momentum A is equal to momentum B? Since they have the same velocities. Okay, so if you're going to take a look at this, we have MA y over T naught, and then we have here MB y over T naught square root of 1 minus v squared over. Okay, looking at this one, we have momentum A equals momentum B. Let's take a look at this. Do they have the same momentum? Since they have the same velocities? If you are going to check this one, they will have the same momentum if there will be a relationship wherein the mass of A is not equal to mass of B. Because if we say that mass of A is equal to mass of B, obviously momentum is not conserved. Because you can see here, there's a factor square root of 1 minus v squared over c squared, which is always a factor less than 1. But if we can analyze now that they will be the same, or their momentum will be the same if and only if mass A is equal to square root of 1 minus v squared over c squared of mass B. Then we can say that momentum is conserved. Okay, based on our calculation earlier, we can also express mass of B. So you have mass B is also equivalent to mass of A divided by square root of 1 minus v squared over c squared. Okay, this factor will make momentum conserved if MB is equal to MA divided by square root of 1 minus v squared over c squared. Therefore, we can say that in relativity, velocity affects the mass of the system. So mass as a function, therefore here, mass as a function of velocity is equivalent to mass divided by square root of 1 minus v squared over c squared. So that will be our equation, where in momentum again, it's still mv. But in relativistic mechanics now, velocity or mass is a factor of velocity, so we now have momentum. Our relativistic momentum will be equivalent to mass, which is mass divided by square root of 1 minus v squared over c squared times the velocity. Okay, so we can actually express this one, the 1 over square root of 1 minus v squared over c squared, then mv, we can express this into gamma mv. Okay, so we now have gamma equals square root of 1 over square root of 1 minus v squared over c squared. So that is our relativistic momentum. Okay? So again, take notes. This one is the gamma. So since